Okay, I'm going to get started. Right, so we have been talking about tangent bundles and higher order tangent bundles, and last time we started, we introduced the notion of a derivative of a mapping between manifolds. So remember the setup is I have manifolds M and N, a mapping between them, and with appropriate regularity assumptions. And then you have what you can think of as being the kth derivative of the mapping phi, which maps the kth order tangent bundle of M to the kth order tangent bundle of N, and it's simply defined by um, since these kth order tangent vectors are equivalence classes of curves, um, we define the mapping as a mapping between equivalence classes of curves, like this. Okay. All right, so we'll have some things to say about that today. Um, but first, let me make a distinction between a similar kind of a construction. Um, and that is, so these are higher order tangent bundles. You can also iterate tangent bundles, and they're different things. Okay, so if I have M, okay, then I can make its tangent bundle. Then I can make its tangent bundle, and let me denote this is T2. Okay, and so on, like this. Okay, so these are different things. Um, and so an example illustrates why. And so, sorry, also you can also iterate tangent maps. Okay, so if I have phi, then I can go T phi, and T phi is just a special case of TK phi. It's T one phi. Okay. Then you can go T phi, which you would call T2 phi, and so on, up to TK phi. All right, and so you somehow think um, that these that TK phi and TK phi should be related, and they are. Oops, sorry. And they are, but the relationship isn't so immediately straightforward. So let me illustrate these various derivatives, and this again goes back to things that we talked about last class. So I've written it out here so I make sure I get all the formulas right. Um, to things we talked about last class with Fa de Bruno and stuff like this. Okay, so I'm going to look at all of this business in the special case where M is an open subset of some locally convex space, and N is a locally convex space. So back in the setting of calculus that we spent the first part of the course in. All right. Okay, so I have an open subset O of a locally convex space U, and I have a mapping, and I'm just going to consider second derivatives. So let's just say the mapping is C2, okay, going from this open subset into another locally convex space V. So we had previously talked about derivatives, of course, and you can sort of think of bundling the first two derivatives together into one thing, which is this mapping that I've written out here. And so it takes um, a point in O cross U, and it maps it to a point in V cross V cross V. Okay. All right, and so all you do is you just list the zeroth derivative, the first derivative, and the second derivative. Okay. Great. All right. So now let's take the same mapping phi and t to it. So there's sort of two versions of t2. I mean the tangent, the second order tangent map. Okay. And so the domain of this thing is going to be the same as in the previous case. So it's O cross U, and it's going to map to V cross V cross V. All right. Um, okay, so in this case, so I wrote this out last time because I actually wrote out the first three derivatives, and the tangent map now looks like zeroth derivative, first derivative, and this is kind of the second derivative term, and so you'll see that it's not just the second derivative that I had from before. Okay, then you have the other T2 version. Okay, so and here the domains change. So the domain here is O cross U. Okay, so that'll be TO. And then I'm going to take T of that, and so that's going to introduce U cross U. Okay, so it's bigger. The set of stuff that T2 phi takes as an argument is bigger. And so here I get V cross V, cross V, cross V. All right, so now the mapping here. So I'm taking T of T phi, right? So I'm T of T phi. Okay, so T phi is going to just be applied to X and U. So I get the derivative, sorry, the zeroth order term, there's the function, and then its first derivative. Okay, so this thing here is T phi. Okay. And then when I go T2 phi, I take T of that. Okay. And so this is a function now of two arguments, of course, X and U. Okay, so it's going to have two components, and I'm going to calculate the derivatives of the components using the partial derivative formula. Okay, so in the first slot here, I'm going to take the derivative of this. Okay, so the derivative of this with respect to x is going to be that thing. Okay, so the v here is the first component. All right, so that's why it's v, not w. And then I take the derivative of this with respect to u, but of course it's independent of u, so that's it. Okay. And then I differentiate this guy with respect to x, then u. So with respect to x, I'm going to get this. And again, it's the v that shows up here because that's the first term here. And then I take the derivative of this with respect to u, but it's linear in u. And so the derivative of a linear function is just the function itself. All right, so you get this. All right. So now these things all sort of seem to contain the same data, but they're not the same. And one of the things that I want to point out here is, first of all, up to first order, they are the same. Okay, so the first order thing is somehow natural. It shows up as being a thing, and it's the same thing in multiple different representations. And so it's all just really T phi. Okay, so that's the first order thing. And T phi could either be, T1 phi, or it can be T1 phi, but those are the same. All right. And so they differ in the second order. And so here, this is just our ordinary second derivative. And here we saw that the Fodor-Bruno formula gives you multiple terms that show up in the second derivative, including first order derivatives. Okay. And then here again, you get second derivatives and first derivatives next, and then you get this sort of seemingly redundant piece of information here, where these are really the same thing. Okay. And so you can see here that if you set, for example, u equals v, okay, so here you take these two to be the same, okay, then you see that these two things aren't just sort of related to each other, but they're actually equal, okay, so those are, and they're actually this, all right. And if you take u equals v, then you get the same thing. You get a repeated thing here, just like you do here. And then you get a first derivative of phi with your kind of extra vector. In this case, it's u2. In this case, it's w. And so you can see that there's really a nice emerging relationship between T2 phi and T2 phi, the different versions of T2 phi. And this can be made formal. And that's because T2 M is a submanifold of T2M. And T2 phi is the restriction to T2M of T2 phi. Okay, so there's all kinds of stuff going on there that I'm not talking about. All right. Okay, good. One additional little thing. Um, uh, this and this seem to fundamentally be different in the sense that this thing takes as its argument the same arguments. All right. And that's always going to be the case. And we saw that in the when we looked at the third derivative as well, that the highest order derivative contains just multiple entries of U1, right? Um, and so you seem to be maybe losing some information as you go from here to here, because this is only telling you what D2 phi looks like if you feed it the same arguments. But here's where you use symmetry. Um, so because D2 phi is symmetric, if you know, say, that this thing is continuous, okay, you can infer that this one is continuous as well. And the reason that you can do that is if you have a symmetric multilinear mapping. Okay, it suffices if you know the symmetric multilinear mapping on a list of arguments that's all the same. Okay, then you can derive the general form of the multilinear mapping using what's called the polarization formula. Okay, so the point is you can express this thing as a finite linear combination of entries like this. So of course, it's not just this, it's not the same U1 and U2. You have to go like U1 plus U2 and then U1 minus U2. But the point is, if you know it on identical arguments, you can figure it out on different arguments by what's called the polarization identity. All right, and so really, these three things really are all different representations of the same thing. Okay, good. I think that's all I will. No, it's not all I will say about that, because there's one more thing I want to point out here. When we had calculus, we had, you know, zeroth derivative, first derivative, second derivative. Okay, so zeroth derivative, first derivative. So we've already said first derivatives are good, and then second derivative, but the second derivative seems to involve the first derivative. And the way the message to take away from that is not that this thing is now your second derivative. That's not the takeaway from that. The takeaway from that is that there is no second derivative. Okay. There is no thing that you can isolate and say, this is the second derivative, like you can when you're working in calculus between open subsets of locally convex spaces. Okay. So the first derivatives are always well defined. Second derivatives are not. Okay. Okay. The thing that is well defined is that. Okay, good. So I think maybe that's all I'll say about that. All right, good. So I think what I want to do for the rest of the lecture is talk about vector fields. Okay. Um, and vector fields are, so we've talked about sections of vector bundles. So if we had a vector bundle, okay, we talked about a section as being a mapping from the base into the total space, so that when you project this down, you get the identity. And as I said at the time, the picture there is that C assigns to a point in M a point in the fiber over M. That's what that formula means. Okay, and so to each point you assign a point in the fiber, and so a vector field is just a section of the tangent bundle. Okay. And so I have a manifold with some regularity, and I'm going to choose some regularity for my vector fields, and that regularity is going to have to be at most r minus 1. And the reason is that the tangent bundle of a CR manifold is a CR minus 1 manifold. All right, so I lose a degree of differentiability when I go to tangent bundles. So a CK vector field. Hmm. And a CK section of, I don't think I introduced this notation. I did talk about the tangent bundle as being a vector bundle, and its vector bundle projection I'm going to write as pi sub tm. Okay, so we talked about the vector bundle structure of the tangent bundle. So this is the tangent bundle projection, or the vector bundle projection, which is called the tangent bundle projection in this case. All right, so that's all a vector field is. And so, if we draw manifolds like this, all right, so um, a vector field assigns a tangent vector to each point, like that. Okay. All right, so that's nice. So that's a nice geometric picture of what a tangent bundle is. But let's look, the vector fields, um, you can do a surprising amount of stuff with vector fields, all right? Um, and so we'll talk about two kinds of stuff that you can do with vector fields. One we've kind of already seen, and the other, oh, sorry, let me do this so I don't fall asleep. Um, and the other will be sort of a new interpretation that we haven't seen before. Okay. Okay. So first, remember that we had tangent vectors. So a tangent vector gamma x in the tangent space at x defines an f, what I call an f derivation at x. Okay. So this is the mapping. Okay, so this is the mapping from the space of functions. Okay, so remember that this notation here means that there's an implied but missing f like this. Okay, so it means scalar valued functions. And it maps to f given by. And the precise definition is that it takes a function, f, and maps it to f composed with gamma prime at 0. Okay, so we spent a bit of time talking about the fact that this is a derivation. And we talked a bit about the relationship between tangent vectors and derivations at x. Okay, so what is there a nice correspondence there? Well, there's not quite. It's not as nice as you would like. So for finite dimensional manifolds, it's a one-to-one correspondence. In fact, it's an isomorphism of vector spaces. But in general, it's not surjective in general. And in general, in other words, the mapping from tangent vectors to derivations is not generally surjective, and it's not known whether it's injective or not. Okay. But nevertheless, tangent vectors are derivations at x naught. And so vector fields are derivations on the algebra of functions. So if x is a vector field, okay. All right, so this is our notation for sections of a vector bundle, is this symbol gamma. All right. So this is a CK vector field, and if f is, let's say, a CR function. All right, and R is going to be greater than or equal to 1. Okay, then we define a function which I would denote LXF on M by, okay, LXF at X is simply going to be, X at X is going to be a tangent vector. And so this is going to be a derivation, or sorry, an equivalence class of curves like this. And so I'm going to write this as it's just the corresponding derivation at x naught. Okay, so f composed with gamma prime at 0. Okay. All right. And so we saw formulas for these things. So if so when we talked about this derivation, we showed that it was a derivation by writing it down in a chart. And if you go back and look at that chart, definition or chart verification of the derivation property, there's a nice formula for this. So if we take a chart U phi phi v phi is a chart for M with so there will necessarily then be an associated vector bundle chart for TM. Sorry. Okay, so this is the natural chart for TM. Okay. Then the local representative of LXF is okay. So it's so this is going to be a function now, and so the local representative therefore is going to be a function defined on the image of this thing under phi. Okay, so it's going to go phi of u phi. So this will be an open subset of v phi. Okay, so it's going to take a point x, and it's simply going to map it to d f phi. So f phi is the local representative of v phi. Um, um, okay, so df phi at x in the direction of x, like this. Okay. So that's what this function looks like. Okay, and so this is the what's called the Lie derivative of f with respect to x. Okay. All right, and so because of the derivation property of tangent vectors, they're the corresponding derivation property of the Lie derivative. Okay. Oh, and so what do we know about this um, function LXF? Well, so first of all, we see that x need not be anything to make sense of this definition. X only needs to be continuous. Okay. And this thing, if the function f is CR, this is CR minus 1. And so this will be the regularity of this will be the minimum of R minus 1 and K. Okay, so usually one doesn't fuss with regularity, and I'm going to stop doing that now. So let's take k equals r equals infinity. Okay, so everything is infinitely differential, and that just makes less bookkeeping. You don't lose anything conceptually by doing that, just you lose some bookkeeping. All right, so in this case, so then the mapping Lx from C, I've already said infinity, is a derivation of the F algebra, infinity F. Okay. And so we talked a bit about what a derivation is generally, but it means that it satisfies some product rule type condition. And so Lx F G is F Lx G plus Lx F G. Okay. All right. And so again, what's the so we for every vector field, we have a derivation, and the derivation is that. Okay. So what can be said about mapping X maps to Lx? Okay. So if M is finite dimensional, it's a bijection. It is generally not surjective in the same way that the association of tangent vectors to derivations at a point are not surjective. Okay, and it's not known whether it is injective. Okay, this is a very similar story to what we had when we talked about derivations at a point. Okay. And so this again is a point of departure from the finite dimensional theory where if you want to if you can show that something is a derivation, then you can conclude that that means it's a vector field, and that's not generally true in infinite dimensions. Okay. All right, so that's sort of an operator version, interpretation of vector fields. Okay, so vector fields act like differential operators. They can be used to differentiate things, and they can be used to differentiate things more general than functions. But we're not going to be able to get to that. All right. But let's talk about another sort of use of vector fields. Okay, so and let me sort of not specify any kind of regularity here. Okay, so I have a vector field on a manifold. Okay. The only thing I know about regularity is that M has to be at least C1, okay, and X has to be of a regularity, which is that of M minus 1. Okay, so let's just take all that for granted. So a curve, oh, so sorry, let me do it like this. Let I be an interval. Okay, a curve, C1 curve, gamma in M is an integral curve, or X if um, gamma prime of T. So I haven't said what gamma prime is. And I guess this, so we've talked about gamma prime for curves, and this is not quite the same thing. Um, okay, so gamma is a C1 mapping from an interval into a manifold. So I can T gamma. Okay. Um, and when I do that, I evaluate this thing at points in Ti. Okay, but I is a subset, and there's some issues about the openness of of I, but let me not fuss about those. And if you want to, just assume that I is open. But anyway, Ti will be I cross R. Okay, so I'm going to evaluate this thing at a point um, um, in I cross R, and the point in I, of course, will be T. And the point in R will be 1. Okay, that's the definition of gamma prime. Okay, and this is not quite the same. Oh, and sorry, just to be consistent with the rest of my life, I usually write integral curves not as gamma. I write curves as gamma, but integral curves, I write them as C. C. All right, and so the formula or the definition of integral curve means that this is x composed with gamma at t. All right, so we have this notion of an integral curve. Oh, sorry, gamma. C. All right. So there's a sort of picture you have in your mind here. Let's say t. Here's c of t. All right, and so at this point, I have two things. I have the okay, because this guy, after all, this thing lives in t c of t m. Okay, so it's a tangent vector, and I write that at sorry e. Okay. But if it's an integral curve, this thing is equal to x at c of t. Okay. And that's true for every point. So let's say my curve C looks like this. Okay. And so at every point along the curve, the tangent vector to the curve is equal to the specification of the vector field at that point. Okay. I have, all kinds of tangent vectors prescribed by the vector field off the curve, but I'm only interested in the ones on the curve. Okay, so that's integral curve. All right. Um, so for, oops. Um, so for this discussion, we're going to consider vector fields, which are going to possibly depend on time and a parameter in some space, a topological space or something like that. Okay. So, and we'll see why that might be interesting. We will consider vector fields depending on time. So time is the thing which I'm writing as t above, and parameter. Okay, so we're going to let, therefore, I be an interval. And let's just say that P is a topological space for the time being. Okay, so then a time and dependent field is a vector field that depends on time and a parameter. Okay, so it's a mapping like this. Satisfying x of t, x, p is in the tangent space at x. Okay, so it again assigns to x a tangent vector at x, but it does so in a way that depends on time and parameter. And so then an integral curve. So I'm going to just adapt this definition in a fairly obvious, this definition of integral curve from above in a fairly obvious way to time and parameter dependent vector fields. Okay. All right, so it's going to be defined on some subinterval, I prime, let's say. And of course, it satisfies the expected formula. This. All right. Okay, so good. So that's what an integral curve of a time and parameter dependent vector field is. So let's get an idea of what these things look like um, uh, by looking at what this formula looks like if I represent it in a chart. So let's let sorry, I think I made a typo. For some reason, I think of it now. Yes, sorry, because I have to do the same thing here. So in this formula up here, I made a typo. That's the principal part of x in the coordinate chart there, of course. Okay. All right, so let C phi be the local representative of C. Okay, so C is a curve. defined on some subinterval of I. It's going to take values in M. And so, I'm making some assumptions about various things here when I'm writing down xi phi. So xi phi is going to be defined for a set of times. So may necessarily be a subset of I prime, but a set of times where the curve takes values in u phi. Okay, so I'm not writing all the stuff down to make sense of that, but you definitely have to do that. And let x phi, okay, this is going to be a map from I cross phi of u phi cross p be the local representative of x. Okay. All right. So then the formula star as the local representation. Okay, so it's C phi prime. And so now C phi is going to be a curve on here, right? Um, and so this prime now, and so there's an abusive notation happening here. This prime is the good old-fashioned prime that we had from before. Right? And you had a homework problem where you kind of deduce the correspondence between the two primes. That was the idea of the homework problem. Okay. Um, and so this is x phi of t, c phi of t, p. All right. And so the role of p here is it's just a parameter. It's not time dependent. And so, when you write down this formula, P is fixed. And then you change phi and the formula changes and you get a different formula, but P is still fixed at whatever value it is that you choose for it. So the interesting thing for the purposes of this equation is t and the dependence on t and the point in phi of u phi. Okay, and p is there because maybe you'd like to consider kind of multiple differential equation, or sorry, multiple vector fields, and they're parameterized by a parameter p, and you would like for the solutions of this equation to depend in a certain way on that parameter. Okay, but I mentioned the word differential equation slipped out, and that's because this thing is an ordinary differential equation. This is an ordinary differential equation on the open subset phi of u phi in v phi. Okay, so it's an open, it's a differential equation on an open subset of a locally convex space. Okay, and it depends on, just like my vector field, time and parameter. Okay, so ordinary differential equations are something, of course, that are well studied. And so this is good news because now integral curves of vector fields are related precisely to some classical object, namely an ordinary differential equation. Okay. The bad news is in locally convex spaces, differential equations are not as friendly as they are. So, probably everybody who's watching this video has certainly seen ordinary differential equations in finite dimensions, at least linear ones. Um, um, and there's a nice existence and uniqueness theory for such things. Um, but for differential equations in locally convex spaces, there is no nice existence and uniqueness theory. And I want to talk about that by considering two quite simple counterexamples. Okay? Examples. And so these are going to be uh, well behaved in whatever sense. Um, Differential equations defined on locally convex spaces, which do not have a nice sort of existence and uniqueness theory. Okay. Okay, so the first example. Um, so it involves something we haven't talked very much about, and that's direct sums. But in this particular case, it's easy to give an explicit definition of what this thing means. Um, so this is going to be the set of mappings. So it's going to be the set of mappings phi from the non-negative integers into R, such that phi of j equals 0 for all but finitely many j. Okay, so that's what this symbol means, and that's what the symbol means too, because I'm telling you those are the same thing. All right. Okay, so this is a locally convex space. Um, 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 we haven't talked about what the direct sum topology is, but the only thing I will say is that, uh, and we don't really need it for the purposes of this example, but the topology on R z greater than or equal to 0 is the so-called direct sum topology. Um, and it's the topology in this case, things are a bit simpler because this is a countable direct sum. Topologies for non-countable direct sums are more complicated, um, uh, which has as its base the set of the sets of the form. So I'm going to take products of, okay, so this is direct sums of R. So I'm going to take products of open subsets of R. Okay, so I'll just write those as UJ. Okay. Okay, so this is a subset of the product. And so this UJs are open in R. Okay. All right, so I take this and I intersect it with the direct sum. because the direct sum is a subset of the product. The product is the set of all mappings like this, and the direct sum is the set of all mappings like this, which satisfy a condition. Okay, so this is automatically contained in the product, and so this intersection makes sense. Okay. Like I said, the topology isn't so important for this example, but that's what it is. Okay. And so in other words, this thing is a locally convex space. All right, so now I'm going to consider a linear mapping. Okay, so from this direct sum to itself. And it's going to be the mapping, which takes, okay, so elements of the direct sum are mappings. And it's going to send it to another thing in the direct sum. So the thing in the direct sum is also a mapping. And they'll tell you what the mapping is. So J is equal to 0. So if I'm at the far left, um, um, I, uh, I assign a 0 to it. Okay. Um, and when J is positive, I assign the thing that was immediately, sorry. Okay. So this is a right shift, okay, because it takes the value at j minus 1 and it shifts it over to the value at j, and then I fill in a 0 at j equals 0. Okay, so this is a is a continuous linear mapping. Okay, and so this is where this topology comes in. If you want to verify that, you have to use that topology. Okay, and so is uh, infinitely differentiable. Okay, so we want to consider now the ordinary differential equation in this locally convex space. C prime is a C, like that. Okay. And it's going to have some initial condition. I'm sorry. Okay, so I start with some element of the direct sum. Okay. Okay, so let's see if we can solve this differential equation. Okay. So first we notice that, so we're going to write Cj of t to be C of t j. Okay, so C of t is going to be an element of the direct sum. Elements of the direct sum are mappings. And so we can evaluate that at a j, and we're going to denote that by Cj. Okay. Then we have, okay, so if you just take this differential equation and apply that notation, you get that Cj prime of t is, okay, so this is now just Cj of t is just a real valued function of the real variable t. So it's a very simple thing. Okay, so applying the definition, this is 0 when j equals 0, and it's Cj minus 1 of t when j is positive. Okay. All right, so you can just integrate this term by term, right? So you first start by evaluating that initial condition, okay? And so at this initial condition, you started off at you read off what Cj at zero has to be. Okay, so Cj at zero has to be phi zero at zero. Okay, and then you just apply the differential equation to get what C1 at um, sorry. Uh, so you can immediately solve the equation for j equals 0, and then you solve it for j equals 1 by just integrating the thing that you have at t equals 0, or sorry, for j equals 0, sorry. Okay. So by direct integration, we have that Cj of t is phi 0 at 0, okay, because that you just said j equals 0 and you read that off, and then you start integrating, okay? Then it's t to the j over j factorial. Okay, and this is valid for any t in whatever interval you're solving the differential equation, and for any j. Okay, good. So we make a few observations from this. Okay. If phi 0, the initial condition, is not equal to 0, then C of t is not in the direct sum for t positive, or not equal to 0, I should say. Okay, why is that? That's simply because if this is non-zero, then Cj is non-zero for every non-zero t. Okay, but for things in the direct sum, this has to be non-zero for all but finitely many j. That won't be true. Okay. All right. So if Vj, sorry, if this is equal to 0, then the only solution, uh, again, just from this formula, is the 0 solution. Okay, so the only solution to, let's call this initial value problem 1, because we're going to have another one in a second. Okay, so the only solution to IVP1 is C of t equals 0. Okay. That's and so in particular, you can see that if phi 0 of 0 is equal to 0, but phi, sorry, 0 of j is not equal to 0 for some non-zero j, okay, then IVP1 still has no solution. Okay, because the initial condition cannot be satisfied um, uh, by um, by this solution, because the solution, when you evaluate it at t equals 0, will be 0. So it won't satisfy these initial conditions. Okay, and so this differential equation here, it has one and only one solution through a single initial condition, and the initial condition is exactly when this thing is equal to identically zero, okay, in which case the solution of the differential equation is identically zero. If this thing is non-zero, okay, then this has no solution. Right? So, good. That's one example. All right. So the other example is similar. Okay. Um, oh, sorry. Let me maybe do this. Okay. So here I'm going to take not the direct sum of countably many copies of R, but the direct product. Okay. Okay, and this is R to the okay, so this is the product. So this is just a set of all mappings phi from with no restrictions like we had for the direct sum. Okay. All right, so on that space, we're going to again define a differential equation. Which is going to be linear and continuous. Okay, so this is going to take some element of the product, and it's going to map it to, so in the previous example, we had a right shift. This is going to be a left shift. So everything gets moved to the left, and the leftmost term just gets chopped off. Okay, so that. Okay, so A is again continuous and linear. And you can check continuity by using the product topology. So smooth. Okay. So we have the same kind of idea about writing down what the differential equations governing the solution look like. Okay. So if again we're going to write Cj of t to be C of t of j, then the differential equation. So notice that this differential equation is time independent. So it's a very simple kind of differential equation. All right. Right. And so we're going to have some initial condition here again. Let's say that C 0 is equal to phi 0, and so Cj 0 will be 0. Oh, sorry, phi 0 at j. Okay, all right. So what we're going to do here is we're going to arrive at multiple solutions of the same differential equation. Sorry, multiple solutions of this initial value problem. All right, so many solutions of this equation which satisfy the same initial condition. Okay, so here's how we're going to do that. All right, so note that. All right. if C0, okay, so C0 is the solution evaluated at j equals 0. And so that's going to be a real valued function of time. Okay, and I'm going to choose this to be an infinitely differentiable function. So we're talking about real differentiability here of R. Okay, then Cj of t. Okay, so this finds the solution at j equals 0, and then uh, we can see that if Cj of t is the derivative of C0, I'm sorry, the jth derivative, okay, then C will um, be a solution of the differential equation. Okay, so it'll solve this equation. Okay, and that's, again, you just directly substitute it into the equation. Okay. All right. So now, why does this violate uniqueness? Okay. So now, oops, if we choose two solutions, C and eta, okay. So we choose solutions C and eta such that oops, such that C0, okay, so the zeroth component of C and eta are C infinity functions, okay, just like I did here, okay, but I'm taking two different ones now, but they have to satisfy um, a condition. Okay, namely they have to satisfy that their all of their derivatives at 0 agree. Okay. All right, so now um, we know then that these things will give rise to solutions like this. Okay. They will satisfy the same initial condition because of that formula. Okay. But if we choose them, C and eta, well, C naught and eta naught, so that these are the same, but but the functions C naught and eta naught are different, then we will have two different solutions to this initial value problem. Okay. Then both um, C and eta, sorry, satisfy, and let's call this IVP2. Okay. But may not be the same. Okay, so in other words, asking that these two C infinity functions, C naught and eta naught, um, asking that they um, asking that they have the same derivatives at t equals 0 does not mean that they're the same. So, oops. So for example, we could take C naught of t to be 0. Sorry. Yeah, C naught of t to be 0, and eta naught of t to be e to the minus 1 over t for t not equal to 0, and 0 for t equals 0. Okay, so these things all have both have all derivatives equal to 0 at 0. Okay, but they're not the same function. And so, this would give you um, the initial condition that would correspond to the fact that all of these things are identically 0. Okay, but if you just take any function, you add something whose derivatives are identically 0 to it, then you don't change its derivatives. And so these can be used to construct all kinds of different examples that satisfy an initial condition like that. Okay, so that's the idea here. And so we have, oops, so we have um, the punchline. ODEs in locally convex spaces may fail to have solutions, and or solutions may fail to be unique. So solutions to initial value problems. Okay. So this is actually a significant problem um, for the theory of general locally convex spaces and doing calculus in locally convex spaces, is anything you do that needs a solution to a differential equation, like, for example, talking about an integral curve, um, because of this lack of a suitable existence and uniqueness theory for ODEs in locally convex spaces, integral curves on general infinite dimensional manifolds, integral curves of vector fields, may fail to exist or have unique solutions given initial conditions. Okay. All right. So, how bad is it? So, in other words, what assumptions do you need in order for this to work? Okay, so these examples had to do with ODEs, and the connection to ODEs comes from the fact that when you represent the integral curve condition in a chart, you get an ODE. All right, so I'm going to state the condition, just to keep things simple. I will not state the condition on manifolds. I'm going to, in other words, not for integral curves. I'm going to do it on open subsets of locally convex spaces, meaning for differential equations. Okay. So this difference in terminology between differential equations and integral curves, it's not always uniform. So very often people will talk about differential equations on ordinary differential equations on manifolds, and they're talking about integral curves, or they're talking about what I'm calling integral curves. So I think the punchline is things work well in Banach spaces. Okay, so let me talk about time and parameter dependent ordinary differential equations. Okay, and if so, let's say I take a mapping f from time. Oh, sorry. I need an open subset O of U. So O cross P into U. All right, so this is going to satisfy some conditions. So I'm going to ask the F be continuous. And for each T naught, X naught, and P naught in I cross O cross P. Okay. There exists a subinterval I prime in I, okay, which of course contains T naught. Okay. A neighborhood O prime or an open subset O prime in O, and of course this contains X naught, and P prime in P open with containing P naught. Okay, so for each T naught, X naught, and P naught, there's certain neighborhoods of X naught, T naught, and P naught, um, such that. Oh, sorry, one more. I need one more piece of data and an L positive, such that. Okay, so P U of F T x1 P minus F of T x2 P is less than or equal to L PU of x1 minus x2. If this holds for every T in I prime, P in P prime, and x1, x2 in O prime. Okay, so those are the assumptions, right? So F satisfies these two conditions. Okay, then the initial value problem, right? Okay, so it's an ordinary differential equation. C of t is f of t, c of t, p, c of, let's say, t naught, x naught, and so we've talked about the parameter here. The parameter is really frozen, so let's take the parameter to be p naught. Then the initial value problem has a unique solution on some sub-interval about um, T naught. Okay. And you can say more than that, but to say more than that requires more time than I have right now. All right, so I have this written up carefully in the course text, because what you can say is not only that it has a unique solution, but that the solution depends continuously on all of its data. So what's all of its data? So it's a data. All of its data is the initial condition x naught, the initial time t naught, the parameter p naught, and the final time t. So you can prove that the that the solution is a continuous function of all of those arguments. Um, and you can prove that the set of T naughts, X naughts, P naughts, and T's for which solutions exist is an open subset of um, I cross O cross P. Okay. All right, so there's more that you can say here, but um, it requires a bit of machinery to write down all the things that you need to do to make sense of that. Okay, good. So this gives you what you would call a local, I'm sorry, a local existence and uniqueness theorem, right? So there's some subinterval on which a solution exists and it's unique on that subinterval. Okay. Um, um, and so, like I said, you can make more global assumptions, but we don't have time for that. And finally, theorem two. Um, so theorem two, so theorem two makes more stringent assumptions, but you get to make a stronger conclusion in terms of how the solutions depend on all of the data, the T naught, the X naught, the P naught, and the T. Okay, so here, if U PU is a Banach space, if I is interval, if P, oh, sorry, um, W is a locally convex space, if P is an open subset of W. So our parameters now aren't in an arbitrary topological space, but they're in a locally convex space, open subset of a locally convex space. Okay. And if F uh, is a mapping from I cross, oh, sorry, again, I forgot the O, apologies. So O in U open, O cross P to U is of class C, K, R. So everything has to be R here because we're talking about curves that depend on a real parameter. You can talk about differential equations where the time parameter is complex and that it's interesting to talk about that, but we won't do that here. Then, okay. So this should be k greater than or equal to 1. Then we have the same local existence and uniqueness conclusion as in theorem 1. Okay, so to be a little bit more clear, that means exactly this. For every T naught, X naught, and P naught, there's a subinterval, an open neighborhood of X naught, an open neighborhood of P naught, so that uh, uh, I have, oh, sorry, so that for every T naught, X naught, and P naught, there's a unique solution of the of this initial value problem. Okay, that's the existence uniqueness conclusion. All right. Okay. And the solution depends on t, t naught, x naught, and p in a ck manner, meaning it's ck. Okay, so it depends on this data. Its dependence on this data is ck. I got my grammar is suboptimal there, but it has ck dependence on those parameters. Okay, so if your differential equation is ck, then the set of solutions is also ck. All right. Okay, so there's lots of stuff you can say about differential equations, but this, of course, has the very strong hypothesis that the differential equations, the states, the x's for the differential equations, reside in a Banach space. So as soon as you go beyond Banach spaces to talk about other kinds of locally convex spaces, then that's when things stop working. Okay, so I would very much like to say more about differential equations, but some stuff is written up in the course notes, so you can read it if you want. And I'll stop there for today. And remember, I said last time that the last two lectures, the ones next week, are going to be a little bit different. So we're going to sort of give an overview of a bunch of topics, and so I'm going to go through those fairly quickly. And so I will show up on Monday and Wednesday next week with pre-prepared material. So we'll get through it faster. And the idea is to kind of give some idea about things you can do beyond the things that we've talked about so far, because there's a lot of them. So we've only really covered the absolute basics of locally convex manifolds in this course, and there's a lot more stuff that you can do. Some of it is geared towards some interesting applications, and I'll say a tiny bit about what some of those applications might be. But we won't be able to get into anything in great detail. So that's going to be the last two lectures. So I think that'll wrap it up for today. See you next week.